This time we are going to talk about Noetherian rings, and the slogan of this lecture is that finite generation is best over Noetherian rings. Recall that we had a spooky example of a ring R over a field K in an infinite number of variables. So K is a field, and we take a ring of polynomials in an infinite number of variables, and then the ideal generated by x1, x2, etc., all the variables in R, is not finitely generated. However, R is a finite free R module of rank 1, and so a module of rank 1, which is finitely generated, contains a submodule I, which is not finitely generated. I want to prove a proposition that relates finite generation of submodules with ascending chain condition. So proposition: R is any ring, M is any R module, and the following conditions for M are equivalent. The first is that every R submodule of M is finitely generated. And second, the ascending chain condition, which says that there is no strictly increasing chain of submodules of M. Strictly increasing chain let's say N1 in N2 in N3, etc. of submodules of M. You may recall that we already worked with ascending chain condition for principal ideals. So here we are generalizing it one step further, and we'll work with strictly increasing chains of arbitrary submodules. So the proof. Going from 2 to 1, let N denote some submodule, and let us try and construct a chain of submodules of M. So, and we know that this chain must be finite. If N is 0, then N is finitely generated. So if N is not equal to 0, then we can take an element N1 in N without 0, and we denote by N capital 1 the submodule of M and N generated by N1. Then if N1 is equal to N, then we are good, because then N is generated by one element. But if N1 is not equal to N, then we can take N2, which lies in N without N1. And then we denote by n capital 2 the submodule generated by n1 and n2 in n. And we continue in the same manner. So if ni for some step I is not equal to n, then there exists ni plus first in n without the subset ni. And then we define ni plus 1 to be the submodule of n generated by n1, n2, etc. through ni plus 1. And so we get a chain of submodules, n1 inside n2. And since n2 is not in n1, this inclusion is strict, etc. And for ni is strictly contained in ni plus 1, because this element ni plus 1 was chosen not to be an ni. And so we get a strictly increasing chain So by part 2, it should be finite. So for example, n sub k coincides with n, and n sub k is generated by k elements n1 through nk. And so n is finitely generated. Finitely generated. For the forward direction, 1 implies 2. We are assuming that every submodule is finitely generated. And let us take any ascending chain n1 in n2 in n3, etc. chain of submodules of m, and we will prove, so we want to show that this chain stabilizes. So define the submodule of n as the union of all submodules ni's. I goes from 1 to infinity. So because these submodules are nested, so n2 contains n1 and n3 contains n2, etc. This union is a submodule of m. And it is proved in a similar way as when we proved that a union of nested ideals is an ideal. And since it is a submodule of m, it is finitely generated. So we can choose generators. N is equal to n1 ... nk, and each generator lives in its corresponding submodule for large enough index. So n1 lies in n capital I1, etc. nk belongs to some n capital Ik. And we have a finite number of indices, and so by choosing the largest, of these I1 through Ik, we can assume that we picked some index j such that all generators n1 through nk live in this level nj. But it means that n coincides with nj, but also nj is contained in nj plus 1, etc. And all these submodules are contained in n. And it means that this chain of submodules stabilize because nj must then equal to nj plus 1, and nj plus 2 must be equal to, and nj plus 1 must be equal to nj plus 2, etc. Because here we have n on both sides. And this is how we conclude part 2. I say that a ring R is Noetherian if every ideal of R so all ideals of R are finitely generated. So this is an example of a non-Noetherian ring. By proposition, it is equivalent to saying that there are no strictly increasing chains of ideals of M. There are no strictly increasing chains of ideals I1, I2, etc. of R. Now we do not assume that they are principal. They can be generated by multiple elements. A short historical note is that this property, this Noetherian property, is named after Emmy Noether. She was a German-born mathematician, and she spent her last years, in fact, in Pennsylvania. She developed the theory of rings, fields, modules, and algebras. She was described as a big contributor to Galois theory, which we will start very soon. And she also somehow has a theorem named after her in classical mechanics, which I find really amazing because from my point of view, from my perspective, I don't know how this theorem has anything to do with abstract algebra. And now let us consider lots of examples of Noetherian rings. So principal ideal domains are Noetherian, and this is because they satisfy ascending chain condition for principal ideals, as we proved, and they only contain principal ideals. So, for example, all fields, all Euclidean domains, Z adjoin I, a field if we take a field F and we take the ring of formal power series with coefficients in F, it will be an Noetherian domain. But there are also other examples, which I will prove later as theorems. So if R is Noetherian and I is an ideal in R, then R mod I is Noetherian. And if R is Noetherian, then the ring of polynomials with coefficients is R is Noetherian. So the first spoiler is relatively easy, and the second spoiler is called Hilbert basis theorem, and I will spend the next lecture proving it. Before I move on to proving the theorem that justifies this slogan, I want to give a warning or a non-example. It is that not all unique factorization domains are Noetherian. So let's take R from the beginning of the lecture. We take a field K and adjoin an infinite number of variables, x1, x2, x3, etc. And it is a unique factorization domain because every polynomial is a polynomial in only finite number of variables. And therefore admits a unique factorization into irreducibles. But we saw that R is not Noetherian because if we take the ideal generated by all variables, it is infinitely generated. And similarly, if R is a subring of S, and S is Noetherian, then it does not imply that R is also Noetherian. Let us continue using this example of a ring of polynomials in an infinite number of variables. So we take R, it is an integral domain, and we can embed it into its field of fractions. This is a field, and therefore it is a Noetherian ring. But R is not Noetherian. So in fact, every non-Noetherian domain is included in a Noetherian domain. And this is an interesting asymmetry because quotient rings of Noetherian rings are Noetherian, but subrings of Noetherian rings are not Noetherian. The main theorem of today's lecture supports the slogan that I formulated. It says that if R is a Noetherian ring, then every submodule of a finitely generated R module is itself finitely generated. For the proof, I will consider two cases. So the first case, when the module in question is free. So M is a free module of rank M. And this case will be done by induction. And the second case, I will generalize to an arbitrary R module M. So the case M equal to 1 corresponds to considering submodules of R, which are ideals. And by Noetherian assumption, all ideals of R are finitely generated. So the case M equal to 1 is done. And now let us assume that the theorem is true for any M greater than 1, and for any M greater than 0, and I want to conclude the case for M plus 1. I want to consider the projection from Rm plus 1 to Rm that takes a tuple of elements, A0, A1 through Am, and forgets the first element, the 0th coordinate, A1 through Am. Then the kernel of pi consists of tuples where only the 0th coordinates can vary and all others are 0. And so it is isomorphic to R. Now let M in M be any submodule. And I want to prove that it is finitely generated. So N is contained in M, which is Rm plus 1. And we have a projection pi from Rm plus 1 to Rm. And I want to denote this composite by rho. So rho is equal to pi restricted to n. Now note that the image of rho is a submodule in Rm, and by the induction hypothesis, the image of rho is finitely generated. And further, the kernel of rho consists of those elements which go to 0 under pi. So it is the intersection of the kernel of pi with n. And it means that it is a submodule in R, because the kernel of pi is isomorphic to R. So the kernel is also finitely generated. And now I claim that if image and kernel of some homomorphism are finitely generated, then this module is finitely generated itself. So claim if rho from n to n prime is any homomorphism such that image of rho and the kernel of rho are finitely generated, then n itself is finitely generated. So proof of claim. If image is finitely generated, we can pick a finite number of generators, and I denote it by x1 through xn, and I lift them to elements x1 tilde through xn tilde, so that rho of xi tilde is equal to xi. And similarly, I choose generators for the kernel, let's say y1 through yl. And now I pick any element n inside n, and I say that rho of n can be written with some coefficients as a sum of xi, so a1 x1 through an xn. So I will denote it as a sum over I of ai xi. But then n minus the sum of ai xi tilde belongs to the kernel of rho. And this is because n goes to the sum of ai xi, and the sum of ai xi tilde goes to the sum of ai xi, because we chose xi tilde to be lifts of xi's. And so, because kernel of rho is finitely generated, we write this whole expression as a finite sum over, let's say, j, with coefficients cj from the ring times yj. And so it means that we expressed any element n as a sum of ai's xi tilde and cj's yj. And so the set of x1 tilde through xn tilde and y1 through yl, this set generates n. So this is equal to n. Okay, so this is the proof of the claim. And now apply this claim directly to our case. So image of rho from n to Rm is finitely generated, and the kernel of rho is finitely generated. And so n is finitely generated, and n is any submodule of m, which is Rm. And so we proved that n is finitely generated by this claim. We will shortly apply case 1 to conclude finite generation for an arbitrary finitely generated R module. And now, second case, M is any finitely generated R module. So let's say that a finite set A in M generates M. It means that if we take R A times, it defines a surjection onto M, surjective homomorphism, which I denote by pi. And let us take any submodule n inside M. Then the inverse image of n inside Ra is a submodule, and therefore it is finitely generated by case 1, because R to the power A is free, but also by surjectivity of pi. This module pi inverse of n surjects onto n, and since pi inverse of n is finitely generated, it admits a surjection from some R to the power, let's say k, for some k, and therefore we have a surjection from Rk to n, and so images of generators in pi inverse of n generate n, because this is also a surjection. And so we prove that any submodule of M is finitely generated for a finitely generated R module M. And so we proved this theorem. And as a corollary or observation, we can say that the class of finitely generated modules over a Noetherian ring is closed under the operations of taking kernels and co-kernels. So we can take any kernel or co-kernel of any homomorphism between finitely generated modules, and they will still be finitely generated if we work over the Noetherian ring. So co-kernels are finitely generated because they admit a surjection from a finitely generated module, like the domain. And kernels are submodules of finitely generated modules, and so by Noetherian hypothesis, they are also finitely generated, because we just proved this theorem.